I'll give you all 3 signals for time. The first one will be at 10 minutes, the second one at 14, and the last one will be at 15.
Excuse me.
You don't need to stop in the middle, you can continue whatever you're doing. I'll just give the sequence.
All right. So, good morning, everybody. My name is Ashley Abreu. This is Gabriel Marshall, and this is Sahib Gonzalez, and we are Team AquaBot. We are making a ROV, which is a remotely operated underwater vehicle, for the main competition. So a quick introduction was the main competition is on June the 20th to the 22nd, that's the next year. And they range in three different categories, which is Scout, Ranger, and Explorer. Of course, we're doing Explorer because it's for a 4-year university, and the other one's for high school and elementary. Now, initially, we looked at other teams, and we wanted to see what type of vehicles were they using, or what other limitations they were looking at. And we came up with different design alternatives. Mind you, that for the competition, we have restrictions are minimum, so we don't have, like, say, a cost limit or anything like design parameters. We just have to get 4 tasks done within a timely fashion, timely manner. It's 5 minutes to put it in the water, and then you have 15 minutes to complete the 4 tasks, and another 5 minutes to retrieve it out of the water. So looking at other teams will go for rather different designs. One of the design alternatives was from Team Algae, and they have something of a similar structure. It's just a square box frame, of course, with a cylinder that would house all the instruments and whatnot. Different motors placed in different locations. One mechanical arm to move anything or fix or just get the task done, and then obviously a little thing buoyancy on top to keep it floating. So apart from that, we came up with something maybe a bit smaller to be able to move and control, keep everything a little bit more compact. That way we have more maneuverability. And also we can move through the tight spaces inside the water. So our first design came up with something like this. So we will only have a cylinder, 2 plates where we'll house all 4 propellers, and then 2 metal rods which would be able to connect our robotic grippers. So for our proposed design, we try to do a little combination, make it a bit bulkier, that way we can make it smaller. So we proposed this right here. It's basically the same design, just a bit more spacious, and in order to make it more compact, and we were able to spin around itself. Finally, we came up to this last design. After we were doing a few analysis and thinking about it a bit more, we noticed that it was not balanced properly, and we needed to have it neutrally buoyant. That way we don't have extra force on the motors or anything for it to keep it afloat or stop it from sinking. So what we did is we just made it a longer tube. We have more of an area in the front, and then we have an extra part on the back just to keep it afloat, so it won't go tilt sideways or anything. And the model, you see the propellers over here, camera inside, LEDs, which were not needed but included, and the robotic grippers on either side. Now, even though the competition didn't call for it, we went ahead and also did a material analysis. We tried different materials, say like PVC, they were going for PVC, stainless steel, aluminum, and titanium. What we did was we checked how deep can we go without it collapsing on itself. Obviously, it would go very far deep, but we calculated by hand using things we used learned in mechanical design, that it can go up to about 600 meters down. But this is, of course, a cylinder pressure vessel, and taking account that we do have a little dome in the front that's made out of acrylic. And we went ahead and compared it to how depth to how much the actual part would cost. So we only did this analysis on the actual cylinder due to the fact that everything else is hollow. So the only thing that would be actually under pressure would be the actual little cylinder. Okay, we did it by hand once, and we wanted to check it by SolidWorks to see if we got somewhat the same. Obviously, there was somewhat a lot of differences in my opinion what we put in the parameters, but it would follow the same trend. Obviously, we have more buildup here because of the acrylic, but overall, it holds pretty well. And SolidWorks was giving us 5,000 newtons per square meter at a displacement of 5 millimeters on the actual just cylindrical part.
Okay, I'm going to talk about the fabrication. The first step within the fabrication was just basically getting the 4-inch PVC with a threaded cap. These are regular 3 inches of PVC that were mounted, that the thrusters are mounted on. There's a stainless steel bracket used about 3 inches long. There's one on each of the 3-inch pieces of PVC. Then these pieces were glued into this is starboard. This is used in boat building. It's a polymer that adheres very well with PVC cement to the PVC. For the next slide, as you can see up here, we added the next two pieces of starboard, glued them all together to get the structure together, and then we replaced these wooden dowels. These would basically act as sort of ribs or stringers and to give the support for the next step. Okay, this was how the wires needed to be ran through the thing, and we went through the pressure vessel, and this would have been the biggest problem we would encounter because this would be the weakest point of water leaking into the pressure vessel through the hose. So the way we accomplished this was we drilled 3.5 millimeter holes through the PVC. We placed 3.5 millimeter female butt connectors through them, already with a wire soldered. And then once we did that, we filled it with resin, fiberglass resin, to take any air gaps or anything like that, to not let any water leak into the pressure vessel. The next step was adding fiberglass resin over the rib stringers, the wooden dowels. We use polyester resin and fiberglass sheets. It's very common in boat building, and we believe that since it will be in the water, we would need to design this with no wood, all fiberglass and composite materials. Last step was once we laid the fiberglass, it was had a lot of cavities and imperfections. We used marine filler, poly filler, a lot of sanding, reapplying sanding to get a nice smooth finish. And then the last step was marine gel coat. Instead of regular paint, again in the marine industry, they use a gel coat instead of paint because it's much thicker and much sturdier and can withstand more impact than regular paint. It does not chip. We had to get a special gun to spray it. It had a 2 millimeter nozzle because a regular paint gun wouldn't spray it. There's about 3 to 4 coats of it on here, at least 3 millimeter thickness of gel coat on it to protect it. Electrical components. Okay. Here we have 2 terminals, sort of like in a boat, where we have 2 wide parallel connectors for the batteries. 11.1 volts is each battery. They're going to be parallel, so we'll have each battery is 5,000 milliamps. 2 batteries will have over 1,000 milliamps. This gives us a runtime over an hour with 2 batteries, about half an hour with 1 battery. The next things, each speed controller, these are speed controllers, 30 amp speed controllers, they're connected to the terminals, and then they're receiving their signals from the 6-channel receiver that's placed here. This is the 6-channel receiver, and just a basic layout of which channel controls what. The left thrusters on channel 1, 2, you see here.
Alright, so now we had to choose a camera, and our obvious choice was the GoPro Hero due to its recording capability inside and also its rechargeable battery. So we didn't have to include any extra wires for the power, and 170 degrees in lens view angle, so that we can widely see where we're going, and also our arms while speaking up and anything in the way. Also, this is what we decided to go with the thrusters due to its low underwater current amp. So since we needed to maintain a low current intake from the battery so that it will last longer. Also, our RPMs were 11,000, which is more than enough to move around. This is our cost analysis. It was pretty much about the same what we decided to go up from the beginning. It ended up being 887. And our timeline, it was pretty much exactly as we were expecting to go with. We'll go with global consideration. The manual labels and everything is going to be in different languages. The charger will also be included with the lithium polymer batteries. And the specification of the limits of ROV will be also placed in US and SI units. We believe that the ROV will be able to go through all the tasks in a timely manner, and will be prepared for the competition. Now, the video.
This is from inside the ROV. This is
From my view.
Oh.
yeah. That's from inside.
He has an actual GoPro on him, and then the machine has working on GoPro too.
Oh, it works.
Hopefully.
Need evidence.
As of now.
Yeah, it could break, right?
Is there a narrative in the background?
Oh no, there was
That's the vacuum with the pool.
pool was being cleaned, so
Pool.
yeah, she lent us the pool, so
We can give you guys a quick demonstration too if you'd like to see it.
oh, because we also have to be able to put it together in a timely manner for the competition. So since it's only batteries and there's no cables to be plugged in, it's just plugging it in and putting it inside, and that's it.
Connect the. The noise you're going to hear now is just the speed controllers looking for a signal from the.
So it won't be alarmed.
Yeah.
All right. No need to be alarmed.
Once I turn on the receiver, it'll pick up the signal. See, we have our claws.
Oh, yeah, you control it from there. Yeah.
We have our claws
Like
on
a
the two
video.
channels that we showed. We have a thruster, right thruster, back thruster, and our vertical thrusters are up and down. So it's fully functional.
Oh, and also we can put extra weight or less weight depending on the salinity of the water. So it's perfect.
And this tether cable right here on this side is just for to get an actual live feed from the GoPro. So, and also extend our antenna from actually being underwater to being over the water, because for obvious reasons we want to get maximum amount of coverage.
When it's a small distance, the receiver will pick it up underwater, but if you're going past, let's say 20 to 50 feet, it loses signal, so you would have to use a tether for the feed.
I guess, thank you.
Okay.
Any questions?
Questions?
So who's gonna go to the competition if you're graduating?
All of us.
All of us.
Oh, okay.
Hopefully. Yes,
That's, I didn't know you were doing that. That's really interesting.
Dr. Tamanto,
Yeah,
Dr.
sure.
Basil? Dr. Basil.
All right, I go first this time. All right.
You get there.
So I'm a little bit curious. You guys did some of the pressure calculations, right? I was really confused in that part, what you actually were trying to do. Sorry. So are you trying to go to a specific depth with that, or you were just trying to pick materials that could possibly allow you to go deeper?
Well, we wanted to know what, since obviously we saw other people, other teams and stuff, and everyone was using we have people that use completely PVC frames,
Okay.
and then others that just went on having metals and plates on it, and we just wanted to see what would be ideal. I mean, the
So I
reason
guess
why
my
I
question
went,
is this, were you designing this for so you're designing it specifically for this competition?
Dual purpose. We
Dual.
also wanted it to be recreational.
Okay.
So if we wanted to go
That's why we
Sure.
check out a wreck,
Okay.
300 feet,
So-
we knew we were capable.
Right, okay, so you're then trying to both design it for this competition and then as deep as you can get it, why not, right, or
Exactly.
something?
Yeah, for the
Okay.
price.
I mean, you never know, if we can make it commercial, then we might not even, we can open a company or something.
Normally,
You can go save the Gulf, right, for BP.
They sell commercial ROVs that are capable of getting 200, 300 feet,
Right.
and they cost about $5,000 to $6,000
Right.
each. We
So, and-
constructed one for 800.
Okay, I got you. So I was just curious because the competition itself is in a pool and stuff like that. I mean,
Yeah.
obviously, it's not meant to be really. It's not going to crush itself
Of course.
in a pool. Of course. So the other question is it actually neutrally buoyant at the moment?
Yes.
Because it looks like it floated all the way to the surface and then went all
No,
the
that
way.
was us testing the.
Okay, so you were actually doing
We
so.
could control
yeah.
the buoyancy with the amount of counterweights that we put in the bottom.
Okay, so you actually kind of balanced it out a little bit. Okay.
That was,
okay.
the video was much longer, we had to short it up.
No, sure, yeah. It just might be
Yeah,
helpful,
which-
you know, maybe in the future, just say, we're not hitting the remote right now and it's sitting flat where it is. I mean, that shows, that goes a long way, right? Because you can kind of fiddle with it a little bit to make it usually work. Again, that's kind of a big,
No, actually at the
Yeah.
beginning, it had too much weight, so we had to remove it.
yeah, right. So you took, yeah, but that's perfect. I mean, you're gonna do that no matter what, so. Did you ever try to pick anything up? Like, how easy is it to control?
It's actually simple, it's very surprising. We
Okay.
thought it would take us a while to get to controls. As soon as he got in the pool and I put it in, I started chasing him around the pool. And it was really easy to maneuver, and super fast.
Okay.
It's easier to play Super Mario.
And then one last thing, so, the materials you chose were solely just based on other marine materials, you didn't, that was kind of the extent of that, or?
Yeah,
Okay.
Well, I just want to, since we do have, there was a global component of this, and if you were to throw this, say, in the sea or whatnot, we wouldn't want anything, we won't want it to withstand, but also not to contaminate. I mean, making it out of any other material that can rust or anything can be harmful. So, and if we wanted to look at the aspect that if this could be sold, then there will be regulations after that.
I would just say, the only thing is, it kind of seems like there's a lot of exposed parts in the motors themselves and things like that. So, for instance, if future you wanted to use it, actually in sea environment, a lot of things can kind of get stuck in there pretty easily. So, I mean, you can probably put some cowling and stuff like that.
The good thing about these thrusters is that they were they're brushless thrusters. They can work submerged in the water because it's low voltage, and they're $7 a piece. If one
Well,
goes
yeah,
bad,
but if it gets stuck
Yeah.
somewhere that you don't know where it is, then
Yeah.
you lose all.
you get a couple runs
So,
out of it,
yeah.
replace them every once in a while.
Sure.
Put a GPS.
Is that it, Dr. Basil?
It's my turn.
Is that it, Dr. Basil?
That's it for me, sorry.
Okay, Dr. Tamanto.
Okay, talk to me about the gripper design. There's motors on the gripper, I
Yes.
assume? Are they, okay.
The servo motors, normally they're not waterproof, so what we
Yeah, so what are
did-
you doing to make sure that
What
they are?
we did was, I opened up each motor and we poured mineral oil inside the motors and then replaced the gasket. The mineral oil is non-conductive. Therefore, once we closed the gasket, it was completely sealed, and the mineral oil, what would happen is, it would counteract the hydrostatic pressure at any depth.
Now,
So
is
this
it at any depth?
Well-
And you've got proof of that?
No, not really, but at the 300 feet we're trying to achieve, at 300 feet, we believe it will definitely
Did
will
you
be.
take it to 300 feet
Not
to
yet.
verify that?
No.
Okay. Another question I have is, does the grippers have, how many degrees of freedom do the grippers have? One. So how are you going to manage a situation where something's laying on the ground and you can't actually get, are you capable of taking the motors and flip this piece 90 degrees to the ground?
No, right now they're mounted fixed, right now because the competition guidelines, everything that we saw was, there was nothing laying on the floor, everything was on a milk crate. extended
So it
to
actually
pool.
had access underneath it?
No,
Clearance.
Clearances?
Yeah.
For announcers for the competition, but if it were to go for selling, then obviously we'll change the.
Okay, and the grip, I noticed that you've got, what, about 2 inches of access
Yeah.
in the competition, is that adequate?
Yeah. Everything is, every item that we're supposed to pick up and take has a looped wire design, so it's placed on a milk crate, it's placed on something, you're supposed to pick it up, take it somewhere, drop it, reach you.
Okay.
So it's not a small thickness.
In the competition, most other RVs used one arm, and a lot of them are just hooks, honestly. And we felt that that was a bit unstable because if you have just one hook, moving in the water itself, the material is going to move, and then it had to be put into intricate places or actually just keep it still so you can actually place, say, a little block cylinder with a little edge on it in between and just stand it on something. So having just a little hook like other, or moving the cylinder is not going to be, it takes forever. And it is on a time limit. We do only have 15 minutes to accomplish all 4 tasks on bottom.
Okay, now, and last question I had is, if you go back to your slide on material analysis slide. That is there. I noticed that you're basically coming down to a safety factor of 1.5. Do all the materials instantly come back to a safety factor at 1.5, or did you force drive back?
No, what I did was, to get this to the safety factor, I just kept, for each material, I would replace the material of the actual cylinder, and I kept increasing the depth differently for each material. Obviously, the PVC, once it hit 600, it was at 1.5. Now, if you go for titanium grade 5, it reached 1.5 after 2,500. So I just kept increasing to see, because I wanted a safety factor of 1.5. So I was looking for that number, and I kept increasing the depth until I got to that safety factor. So obviously, with these other safety factors, with lower depth, there was higher safety factor.
Yeah, unfortunately, that slide, I would have at least put marks on there to indicate where I finished up, because it kind of looks like it does and cuts down, and everything runs out to 1.5.
I mean, I just wanted to just point out that that was actually we just wanted to hit one.
That's the threshold.
We just felt that anything less would be
Right.
risky.
Okay, thank you.
That's it, Dr. Tamonte. My question relates to all the penetrations in the body. As the depth increases, the pressure increases, are you sure that those penetrations will not leak with increased pressure due to depth?
That was our main concern. That's why we chose to look here. We extended out a piece of PVC, drilled exactly a 3.5 millimeter hole for the female connectors, made sure that they were very snug in there, and then after we did all that, we filled it with fiberglass resin to give it extra stability to make sure that nothing would leak in there. I believe if we were to have a problem at depth, would be for the clear dome before any of the penetrations of the wires.
And what about all those loose wires? Again, the same question, as pressure increases, what impact with drag and all of that would those wiring experience or sustain?
That's why the reason that they're in the back, because this is where all the thruster wires connect inside the hull. They won't experience any drag force because all of these always going to be going forward and turning around. The only problems would be with the tether. The tether is what produces the most drag at depth. That's why we chose to limit our tether to only 3 small wires and not a power cable, because it would have been a thicker wire for a higher voltage, and that would have increased the drag. So we chose a very small Cat 3 telephone cable wire with 4 individual wires. We're only using 3 of them to keep our drag as low as possible.
And that kind of wiring would resist all those drag forces
It would
with increased depth?
Well, not tested, but for the competition, knowing that the pool is not 20 feet, it would resist for the competition. As for having let's say if we were to take it commercially, we would have to take more testing into account.
Okay. During the testing of the pool, the tether didn't play any problems, pros and
It was
cons.
almost, if you saw the video, it was almost invisible.
Okay, you've answered my question. All right, are there any other questions? Sounds good. Well, thank you. Mia. Clock. All right, group 2, get ready, please.